What is AI and machine learning? Back in 1956 at the Dartmouth Conference in New Hampshire, this term was conceived, and since then, progress has been relentless. Now, in 2025, it's powerful enough to compete against humans and maybe even win. But how did we get here? Let us rewind. Machine learning is kind of like how you and I were taught to learn by our parents, by getting beat up. In other words, what is learning? Well, learning is the process of training on data until expertise is achieved. We humans learn in different ways, and from that same perspective, we design machines to do the same. Machine learning can broadly be classified into three categories: supervised learning, unsupervised learning, and reinforcement learning. Now, let us start by understanding algorithms that enable learning through a supervised paradigm. Supervised machine learning is when a machine is trained on labeled data. Essentially, the machine gets a chance to look at both inputs and outputs in a dataset. From there, it learns how to predict an output based on a given input. The predictions it makes can fall into two categories of values. These are discrete values and continuous values. Continuous values are numbers that exist within a range, like the value of pi, or something more abstract, like the value of a feeling. Discrete values, on the other hand, are fixed, like the number of cars in a parking lot or the color of a fruit.
Now let's start by visualizing how these values could be plotted on a graph in order to start making inferences. On a two-dimensional graph with x and y axes, the x-axis is in charge of representing the independent variable, and the y-axis plots the dependent variables, or the values that change in response to x. Let's solidify this idea by taking an example of a plant's growth. In order to measure the growth of a plant, we first plot the time on the x-axis and the growth on the y-axis. The time is an independent variable, and the growth of the plant is of course dependent on the time variable, hence it is plotted on the y-axis. On measuring the plant's growth over a couple of days, we now have a set of observations. Based on these observations, we can start seeing how much the passing of each day affects the plant's growth. This change in one variable with respect to another is the slope. Simply put, the rise of a variable on a y-axis divided by the run on x-axis gives us the slope, which is also referred to as m. Now that we have a bunch of data points, we can perhaps start predicting the plant's growth instead of having to record it each day. Now how do we do that with as much precision as possible? The idea is to fit a line through the data points in a way that the distance between the data point and the point on a line is minimized. This process of fitting the best line over data points is called linear regression. Let us look at the mathematical derivation for linear regression so that we are prepared to use it for real-life scenarios like predicting house prices. Linear regression starts with the definition of a line, which is simply y is equals to mx plus b, or in other words, function of x is equals to mx plus b, where m is the slope as previously discussed and b is the intercept or the point at which the value of x is 0. Another definition of intercept is where the line intercepts the y-axis. In higher dimensions, this line could be a hyperplane, but we will leave that for future videos. Linear regression is used to predict continuous values. When we have these values plotted on a graph, we could start inference on these points by simply plotting a line with random slope and intercept values. This line is called the poor fit line, since at this point the squared sum of the residuals are now minimized. Remember that the dotted lines show the residual values, which is the value from the point on the prediction line to the actual data point. We simply square these residuals so that positives and negatives do not cancel out. This squared sum of residuals is also known as the error value. The predicted values are represented using y with a hat on it. The actual values are just vanilla y's. After summing all the errors and taking an average of it, we get a cost function. On doing a partial derivation on the slope and intercept values to minimize them, we get the following results. Partial derivation is a tool or a technique that enable us to look at complex function and see the change in only one of the function's variable while the other remain constant. After all that, we get a solution that helps us plot linearly regressing line for a single variable. In real world, this concept is extended for multivariate functions, also known as multiple linear regression. We will take a deeper look at these models as we move along in our machine learning journey. This marks the end of episode 1. Please like, share, and subscribe to show your support. Goodbye.